Here we go. Let's take a look at today's lesson. We're going to look at area approximation Riemann sum. So when we first started talking about integration, some time ago, I explained that it is impossible to integrate every single thing, right? It's not possible, unfortunately, to integrate it by hand. So there had to be some approximation techniques that were created to be able to handle that problem, that we can really integrate anything. And some of the original approximation techniques had to do with Riemann sums. So let's look at the Riemann sums. Riemann sum, so what this mathematician came up with was a technique to, he is estimating the area under the curve. So an integral, one use of an integral is to find the area under a curve. You have probably heard that before. That's one use. So this technique, he came up with this, procedure where he would split the area under the curve into rectangles, a bunch of different rectangles. That's a Riemann sum, when we're splitting the area into a bunch of different rectangles. So it's a right Riemann sum, or a right corner, if you notice the function, so that the very top of the rectangle, we know how to find the area of a rectangle, right? Length times width. It's pretty easy, which is probably why he used rectangles. That's pretty easy. So a right Riemann sum, or a right corner, is where we put, this one's kind of hard to tell, the right corner of, see how the right corner of that top of the rectangle is on the curve? That's the height value we're going to use. The height is going to be, of this rectangle, is going to be calculated by the right corner. Okay, that's a right Riemann sum. If we're looking at a left Riemann sum, then it's the left corner of our rectangle that's going to determine what our height is. So that's the importance of it. It determines the height of the rectangle. We're going to be doing length, width times height. So that's a right Riemann sum and a left Riemann sum. Well, there's also such a thing as a midpoint Riemann sum, and that's where the midpoint of this, the height of this rectangle, the midpoint is how we're going to determine the height of the rectangle. Okay, it's the midpoint. So those are our three options for Riemann sums. We either would be asked to do a right Riemann sum, a left Riemann sum, or a midpoint Riemann sum. Well, that's not the only type of approximations that we have. We also have something called a trapezoidal sum. No, the mathematician that came up with this is not named for them. They're probably really upset about it. Like I came up with trapezoidal sum and my name's not on it, like Riemann sums. But at any rate, trapezoidal sum is simply just using a trapezoid. We're using a trapezoid to approximate the area under the curve rather than a rectangle. That's the difference. It's just using a trapezoid. I mean, visually it looks like that might give us a better estimate. Maybe that's why someone came up with that. It'd be a little bit better of an estimate than some of these. But that's an additional way that we can approximate area under a curve. There are also other vocabulary words that we need to be aware of. The lower sum and an upper sum. So let's talk about what that means. So lower sum. So let's say, for instance, I have an increasing. Let's just talk about increasing curve. We're going to look at these two options. So I have this curve right here. It's increasing. Let's just use a different color so it's clear. So we're going to look at this increasing curve and this one. Okay. If I wanted to do a lower sum states that I need to use the smallest y value on the interval to use as my height, the smallest one. So if I'm on an increasing function, which one of these do you think would be the lower sum? The right Riemann sum or the left Riemann sum? The left one, right? It's the smaller one, right? It's got space underneath there. Okay, so my upper sum would be to use the largest y value possible. The largest y value possible, which would be this one. Would overestimate, right? An upper sum. So that's kind of maybe a way to think about it. Is a lower sum is an underestimate. It's lower than the actual, because these are estimates, right? These aren't exact. And a upper sum would be like an overestimate. So that's going to be an important concept with us on the test, is an overestimate and an underestimate. And it really depends on whether you have an increasing or decreasing function. That's what it depends on. Okay? So those are the techniques we're going to look at today. All right, so yes, it is a calculator lesson. Hopefully you have your calculators with you. We're going to talk about some different techniques. Calculators are going to be important. So let's look at our very first example. So we have the temperature of the water in a tub at time t is modeled by a strictly increasing, okay, this is important information. So this is a strictly increasing function. It only increases. It's twice differentiable. Well, that just means we could take the derivative of it twice. I just keep in the back of our mind, but this strictly increasing is going to be important. And its name is W. It has a name. We cannot change its name because we don't like W. We cannot use F. Do not change its name, okay? When we write it, we need to say W. We're, again, prepping for the AP test, right? When they call it something, you need to call it what they call it. If it's W, we call it W. We don't call it F because, like, everything is f of x, right? No, not on the AP test. Everything is not f of x, so W. At time t equals 0, the temperature of the water is 55 degrees, which it looks like they've given us here. The water is heated for 30 minutes, beginning at time t equals 0. Values of WT at selected times for the first 20 minutes are given in the table. So we have just some tabular data. Very typical of an AP question. This is actually an AP prompt, or part of one. Let's look at part A. So it says for 0 to 20, the average temperature of the water in the tub is, and they give us this formula. So now this is actually a pretty cool formula that we're going to be looking at in a little while, in a few days. This is called average value. This is the average value formula that they're giving us. That's fantastic. They're just giving it to us. We want to integrate this and use a left Riemann sum with 4 subintervals indicated by the table to approximate. I have to draw a picture. I always do. When it says 4, subintervals, I get a little confused looking at the data. Do you have to draw a picture? No. I'm just going to because it helps me. So I'm going to just do my x-axis is actually going to be t for time, so 0, 4, 9, 15, and 20. I'll just draw that out there. My y-axis needs to go to 20. Alright, so we'll just go 5, 10, 15, 20. Let's just, do that. Just go by 5s. So I'm going to draw these rectangles. Now here's the key to draw the rectangles. I need to use the left corner. First of all, 4 subintervals. Can we clearly see where the 4 rectangles are going to be once I draw it out, right? I want to have a rectangle here, 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 and there. Right? I got 4 rectangles. Okay, so in order to decide how high to put the rectangle, I need to pay attention to which Riemann sum it's telling me. The left Riemann sum. So if I'm going to have a rectangle here, which side? The left would be this side, right? 0. So I'm going to draw it at 55. Oops, I had this in the wrong. So this goes 55 to 70. Let's fix the scale over here. So what? We'll start at 50. We need to go to 70, so 50, 55, 60, 65, 70. Okay, we'll just start there. There's a break there. Okay. Alright, so I have to decide, do I use 55 or do I use 57.1? I have to make that decision. And that all depends on which type of Riemann sum I'm doing. I'm doing a left Riemann sum, so I need to use a 55. So my rectangle would look like this. If I was doing a right Riemann sum, would my rectangle look like that? No. It would be drawn at 57. The height would be 57.1. We understand the distinction here? So it just depends on which kind you're asked to draw. So now this one, I'm going to use the height at 4, right? Because that's the left side, and that is 57.1. So it would be like right here. Then on this rectangle, I'm going to use the 9 as my height, which is 61.8, so like about here. And then on this rectangle, I'm going to use the 15 as my height, which is 67.9. So something like that. Okay, there's my rectangles. Okay, so that helps me. Now, let's talk about finding the area and what we need to show. Do not put the area in each of the rectangles and then give me an answer. I can't tell you how many papers, how many tests I scored this last year that did that. You don't get any credit. You have to show the products and the sums. Okay, so here I'm going to show you the minimum work you need to show. I know some of us are minimalists, right? Or maybe we're trying to conserve energy. I'm not really sure. But some of us do not want to necessarily write everything down. Let me show you exactly what you have to write down to get all the points. Okay, so you want to write this integral. So 1 over 20 integral. They love integrals. Write integrals. 0 to 20 w of t dt is approximately. Okay, we're just setting up our stage. If you write equal there instead of approximately, it's okay. It's all right, but it's technically approximately. So the 120 is going to be multiplied by the whole thing, right? So now what I'm going to do is I have to write these numbers down. Here, I have to write them down. So let's see. So this width, that's 4, right? The width of my rectangle is 4 times my height. My height, we decided, was 55. Plus the width of this rectangle, what is that, 5? And that height, the height is at 57.1. Plus the width of this third rectangle between 9 and 15, what is that, 6? Is 6. And the height of this rectangle is 61.8. Plus the width of this last rectangle, that's 5, and the height of this last rectangle is at 67.9. Okay, that's the work you have to show. You don't need to show any other work besides that. You can stop and just put it all in your calculator. But you have, see how this is showing the products and the sums? In order to get credit for it, and there's going to be a question like this, there typically is, in order to get credit for it, you need to show the products and the sums, products and sums. That's what we just did. So we show that, and then we just stick it all in our calculator and write the answer, which is 60.79 degrees Fahrenheit. Okay, and that's our very first Riemann sum. It's a left Riemann sum. So let's think about this for a second. It says, does the approximation overestimate or underestimate the average temperature? We just calculated average temperature. That's what we did with this integral. We got the average temperature between 0 and 20. The average temperature is 60.79. So under or overestimate, okay, so let's talk about this. So I'm actually going to draw the function. We're at 55 at 0, and then 54. It's the left Riemann sum, right? So the function looks something like this. Okay, we can visually see this is an underestimate. Our justification can never say because the rectangles I drew were underneath the curve. No, that doesn't get you any points. Don't do that. Okay? Why do we, it needs to be a mathematical reason. That's not a mathematical reason, that's in a drawing. I'm just drawing things. What's the mathematical reason? The mathematical reason is I have a strictly increasing function, right? I have a strictly increasing function and I'm using a left Riemann sum. That means it's an underestimate. That's what we need to say. So it's an underestimate because we have a strictly increasing function w of t, and we're using a left Riemann sum. That's what we say. That's our justification.
You say like a strictly increasing interval, it's not the whole function.
So, good question. If they ask us this question, they're either going to restrict it for us They're going to restrict the interval for us and just say so that it's either strictly increasing or decreasing, or they're not going to ask us the question. They're never going to ask us the question if we have a mixed increasing decreasing function unless they restrict it in some way, because we can only answer this question if it is strictly increasing or strictly decreasing. So that they would restrict it or they wouldn't ask it. Okay, how are we on our very first Riemann sum? Yes.
And the number 71, like the percent how much money that's
Yes, and it's very sad about it, by the way. The 71 doesn't get to come out and play. I mean, it just stays there. Why didn't we use the 71? That would be, we're not doing the right Riemann sum. If we did a right Riemann sum, we would use the 71, right? And what would we not use if we were doing a right Riemann sum? We wouldn't use the 55, right? So it depends on which one they ask for. It really does. It depends on which one they ask for. Yes. So basically, adding them up and dividing. So we have more than 5 things, right? We have this at 55, but it's a continuous function. We have all of these different values between the whole thing, right? We have, and our interval spans to 20. It's not just 5, right? There's a whole 20. If we were just looking at integers, we would have 20 integers we could divide by, which is basically what this formula is doing. It's dividing by 20. It's taking the entire, interval and dividing by that entire number. Okay? Other questions? Okay, let's look at the next problem, our second and last problem. If we flip through to change that, go to the different page, please. Second page. Come on. Okay. So let's see. We have a car traveling on a straight track during the time interval 0 to 60 seconds. The car's speed measured in feet per second is a continuous function. Okay, that's important. The table shows selected values of the function. Great. All right, so we have another tabular problem. Estimate the distance traveled by the car during the 60 seconds by using a right Riemann sum with 6 subintervals determined by the table. Okay, here we go. I have to draw it again. You don't have to, but I really recommend you drawing it out at least at first. So let's see, what do we have? We have our time goes from 0, then we have, 15, 25, 30, 35. We skip to 50 and then to 60. Our speed goes up to 30, so just do it by tens, 10, 20, 30. Okay. So now we're going to, I would encourage you to draw the rectangles. We're doing a right Riemann sum with 6 subintervals. As I draw this out, it's very apparent what my 6 subintervals are, right? We have 1, 2, 3, 4, 5, 6. I can see the 6 rectangles. Kind of visualize that. So I'm doing a right Riemann sum. So am I going to use the speed of 20 or the speed of 30 to draw my rectangle? 30, because it's the right side, right? This is the right corner, the 15. That's going to make me draw my rectangle. There's my first rectangle. So again, I'm using a right Riemann sum. So for the second rectangle, I'm going to go to the height for the 25, which is at 20. And then for this one, the right side would be at 30, which is at 14. Then let's see, 30, 35, we're at 10. At 50, oh, poor little, there's nothing, there's a 0. And then at 60, it's at 10, back at 10. Okay, so that's what our rectangles look like. Okay, and we're never going to write numbers in them, right? We're not going to do that. Avoid, avoid. We're going to write it out like we're supposed to. This is the integral from 0 to 60 of, 60. Do we have a name for this? Does it give us a name? Doesn't, does it? So we're going to make up we get to pick our own name. Okay, so we're going from 0 to 60. Let's see, we'll name it, or actually, better yet, let's just, it's velocity. I mean, that's what we're integrating, right? We're integrating, this is velocity. So why don't we just call, it's actually speed, but, okay, it's approximately. All right, so let's see. Let's work on each piece. So the first one is 15 wide times our height here would be 30. That gives us the area of our first rectangle, plus. The next one is, what is that, 10 wide, and that height is 20, plus. Are we getting a pretty good idea on how to set those up? Can I just write those down? Are we okay? We see how that happens? Yes.
On the first question,
Mm-hmm. Yes. So here they're not asking for the average distance traveled. That 1 over 20 in the other problem was for an averaging kind of situation. They're not asking for that here. They're just asking for actual distance. All right, so 15 times 30, 20. So then we have 5 times 14 plus 5 times 10 plus 15 times 0 plus 10 times 10. See how I am writing the products and the sums? We see that? Okay, that's significant for the work on our AP test, products and sums. So now we just stick all that in the calculator and we get 870 feet. Now I want to kind of do a little side note right here, which is always, you know, when I first learned calculus, it was so very confusing to me. What we just did, this is speed, right? Oh, this is time, and the other one, so this is the time, and this is speed. And I just kind of racked my brain. It's like, how in the world do I get distance out of an area? It didn't make any sense to me. Area is 2-dimensional, distance is 1-dimensional. What in the world is going on? And I would just ask all kinds of people, how is area distance? And they would just stare at me like, because it is. And I'm like, no, I need to understand why. Why is area distance? And I really didn't ever get the answer. But I finally figured it out. I mean, it took some thinking to figure it out. How is area distance? Well, if we think back to a formula that we learned in, middle school, distance equals rate times time, right? I have my time here and my rate here. Do you see how that's the product of those two? Distance is this area. And it was like, ding, 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 I understand now, because that really made absolutely no sense to me, how area could be distance. This is why, because we are integrating, we're finding the area under the curve of a rate times a time, which is this right here, that's giving us distance. Okay, that's why area is distance. Whew, that was like a light bulb. Finally, I kept asking why. Nobody could answer why. I need to know why. So, yes.
So in the last integration equation, there was like a 1 over 20.
No, because, we don't. Because that was an averaging one. This is not averaging. It's just regular. Uh-huh.
If it's like if you draw the function,
Yes.
kind of the half of the last box, does that mean that's increasing?
So what we have, we have a decreasing and increasing function, so they will not ask us about over or underestimate, because we have a mixture, right? It decreases, then it increases, so we're not going to get that question unless they restrict it. All right, so the last part B says estimate the distance traveled by the car from 30 to 60 seconds. Look how important it is to read instructions. Ooh, they changed numbers on us. They went from 0 to 60 to 30 to 60. If we didn't read instructions, we would miss that. So we are looking at the integral from 30 to 60 of velocity. It's going to be approximately. Okay, I got to set up my picture because I have to draw a picture. So here we go. So we're going from 30, and then we have 35, and then 50 and 60. Okay, we got that. So we need, it's our time. So our speed goes, let's see, the highest is 14. So we'll put that at 14. Okay, we'll do something like that. So, okay, so we're doing a trapezoidal approximation. Looking at this, I can see 3 trapezoids here, right? 3 trapezoids. So my the 30 is at 15. Excuse me. The 30 is at 14. So here's my first side of my trapezoid. The 35 is at 10. So there's my first trapezoid. Okay, the left side is at 30, the 30 seconds is at 14, and then at 10. Okay, there's my first trapezoid. My second trapezoid, this is that same side, but 50 is 0, so it just doesn't look like much of a trapezoid, but we're still going to use trapezoidal to work it. And then this one, the 60 goes to 10, so it looks something like that. Okay, so that's what we're going to be working with. All right, so we may or may not remember the formula for the area of a trapezoid. I'm sure we all remember, but I'm just going to write it down in case, in case we don't. So if you recall, the area of a trapezoid is 1/2 base 1 plus base 2 times height. That's the area of a trapezoid. Now we're going to look at these trapezoids a little differently than we normally would. I want to really kind of point that out. So we're going to call this base 1 and this is base 2. So it's kind of tipped on its side. Okay? And then this one is actually going to be our height. Think about the difficulty if I didn't do it that way. I would have to figure out this, and we don't have time for that. We don't have time for that. This is just an estimation technique. So that's the way that we use base 1, base 2, and height. All right, so let's start writing it down. So since all of them are 1/2, I'm going to factor that 1/2 out. I hope that's not too troubling to us. Instead of doing it for each of the 3 is going to have a 1/2 in it, so I'm just going to factor that out. And I'm going to deal with base 1. So base 1 in my first trapezoid is 14 plus base 2 is 10. And my height, which is this, is 5 plus. Okay, let's look at our next trapezoid or trapezoidal looking thing. So here this height is, what did we say, the base 2, which becomes this trapezoid's base 1 is 10, and the second base is 0. And the height of this, the difference between 50 and 35 is what, 15 plus. Sorry, I kind of ran out of room. Then my last one, I have 0 plus, this last one is 10 times my width is 10. Okay. So then I put all that in my calculator and I get 185 feet. And that is our first look at the first of our approximation techniques. Okay?